Segment 5A, the phases of the moon. Before we start discussing this segment, let me just make the point that observation is very important here. You should be noticing the phase of the moon. Go outside in the evening, notice where the moon is in the sky and how full it is and which side is lit. Go out in the morning and notice the same thing. I could ask you at any time to start from the phase of the moon today when trying to figure something out. Please take notice of this. It's one of the fundamental things in nature that you can enjoy your whole life, and it's important to start doing that now. The key concepts in this segment are as follows. Sunlight reflects off the moon to give the appearance of changing phases. The light we see from the moon is sunlight, and it's reflected off the surface of the moon, even though the moon is not extremely reflective itself, and this is what we're actually seeing. You can prove this by taking a spectrum of the moon's surface and seeing that the spectral characteristics of the light coming from the moon are exactly those coming from the sun. The phase of the moon depends on the position of the moon relative to the Sun-Earth line, because you're seeing the illuminated portion at any given time. The peak altitude of the moon varies with the seasons because the moon is moving along the ecliptic plane. For the full moon, it's pretty easy to figure out what it's doing because the full moon is opposite the sun. The moon rotates once per orbit, so the same side is always facing the Earth. The pattern of craters and oceans, mare, that you see on the moon's surface is always the same because the moon keeps the same face towards us. This illustration, there'll be two, so we'll go through this twice, gives you some idea of the phases. We're sitting on the Earth in the middle of the picture here, and you see that when the moon is on the same side as the sun, we have the new moon because the illuminated side of the moon is facing away from us. Also, at this time, the moon rises and sets together with the sun. At first quarter, about a week later, the right-hand side of the moon, as you look at it, is lit up. That's the side towards the sun. And as the sun is setting, the moon is highest in the sky. Another week later, we have the full moon. The moon is now exactly opposite the sun, and the side that's we're looking away from the sun. We see it. It's midnight when the full moon is at its highest, and we're looking at the fully illuminated side of the moon. A week after that, we're at the third quarter or last quarter, and now it's the left-hand side of the moon that's illuminated because the moon has risen now before the sun does, and when the sun is just rising, we see the moon in its highest point in the sky. This illustration, and I would take some time to come back to this one and look at it again, stop the video here and take a good look, shows photographs of the moon's surface together with the same illustration. So up-down is the day-night line on the Earth, and you see the different phases of the moon illustrated. If we start on the left this time, at the full moon, you notice that in this illustration the light from the sun is coming from the right in all the illustrations. We're at midnight on the Earth and we're seeing the full moon. As we move to the bottom of the picture, to third quarter, we're at 6 a.m. The moon is sunrise. The moon is straight overhead from our line. It's straight from where we're standing, and it's only half of it is illuminated. At noon, as we move around to the right side, we only have the new moon straight overhead. The sun is directly behind the moon. It's not exactly behind the moon, but close. We'll see about that in a little while. And then going to the top of the picture at 6 p.m. at sunset, the moon is when the moon is overhead at sunset, the right half of it is illuminated. It's in its waxing phase at first quarter. Going to an outside view again of the Sun-Earth system, we've seen this illustration before. This is showing the ecliptic plane and the position of the sun relative to the celestial equator at different times of the year. The full moon is directly opposite the sun. So when you're at the summer solstice, the sun is 23.5 degrees above the celestial equator, and the moon is 23.5 degrees below. So here, where the sun rises almost straight overhead on June 21st, the moon only rises to about 37.5 degrees at the nearest full moon to that. Whereas on December 21st, when the sun is only rising to a bit above the horizon, the moon is rising to almost straight overhead when it's full. Now, just as we had a difference between the sidereal day and the solar day, we have a difference between the synodic month, the month of phases, which has to do with when the moon is opposite the sun, and the month relative to the positions in the stars. The sidereal month is shorter than the synodic month, and for the similar reason, and that is that as the Earth moves around the sun, the sun is now in front of different stars a month later, and the moon has to move a bit farther along its orbit to get back in front of the sun from when it got back in front of that same set of stars again. So let me just promulgate a few rules. These may help you when you're trying to think about all of these spatial relationships, to have them to confirm that your spatial relationships are right. I urge you to try to think about this in space and only go to these rules when you have to patch up your thinking. But the sidereal month is 2 days shorter than the synodic month. The month of phases takes 2 days longer than the month to get back in front of the stars. The moon moves to the east with respect to the stars. So the moon rises in the east and sets in the west every day, but relative to the stars, it moves to the east. The moon rises about 50 minutes later each day, and the moon can always be found within 6 degrees of the ecliptic plane.